become an interesting machine learning challenge to make the IBO gate more efficient and make it run faster. And so the IBO gate is basically controlled by 12 different real numbers, which are sort of shown in this diagram here. It doesn't really matter what they are. But the goal is to adapt these parameters now. And the first people to do this, Peter Stone et al., they did it by finite difference policy gradient, just like we just described in the last slide. And then what they did was they basically just ran these robots backwards and forwards along this field and measured how long it took them with each gate. It gave them a few walks up and down and measured how long it took. Did that for each of these 12 dimensions separately. And then, so you have to run it up and down to get one dimension, run it up and down again 12 times to get just one gradient update. You adjust your parameters in that direction and iterate this process until your grad students collapse of exhaustion. And so they did this, and let me see if I can pull up some videos. So this is at an early stage before it's really been trained, and I think what the main thing to notice is that it slips a lot. That this thing is really dependent on the ground which it's on, and it tends to slip an awful lot. And over time, it starts to learn something a little bit better. This one. Uh-oh. Oh no, there we go. Let me try that again. I think that was just an artifact. No? But you can see it's learned this much better gate that deals with the slippiness of the surface much better, and it can move much, much faster. So this was just by adjusting the parameters in the direction of the gradient in a very naive, straightforward way, and some limited number of iterations were sufficient to make progress in this domain and actually figure out a reasonable gate. Now, if you move to higher dimensions, these numerical methods tend to collapse. And so what we'll consider for the rest of the class is how to analytically compute the gradient so that you don't have to laboriously compute this gradient separately for each of your dimensions. Okay, so we'll start with the simplest approaches, no value functions yet. That's the Monte Carlo approaches, and then we'll come back and we'll bring value functions back into the picture. Okay, so we're going to use the following idea, which is we want to compute the policy gradient analytically, and what we're going to assume is that our policy is differentiable. It doesn't actually technically have to be differentiable everywhere, it only has to be differentiable when it's actually picking actions. So if you have some non-differentiability but you're not actually ever picking that action, that's okay. We're also going to assume that we know the gradient of our policy, that we're in control of our policy, something like again, it could be a Gaussian policy or a softmax policy, we'll see some examples, or a neural network, and we know the gradient of this thing because we've created it. And what we're going to use is a trick called likelihood ratios. And the likelihood ratio trick, I'm just going to put it up in isolation, because what we're going to see is pretty much for the rest of the course, this magic gradient of the log policy term is going to appear. And I think it's useful to understand why this gradient of the log appears, because otherwise you'll just be scratching your head saying, why are we suddenly looking at the log of the policy, not the policy itself? And it basically comes up just from this following likelihood ratio trick, where what we're going to want to do is we want to take the gradient of our policy, we want to understand the policy gradient, and we're going to want to take expectations of that thing. And so the way we do that is we basically note that we can multiply and divide by our policy without changing it, and that this term over here on the right, the gradient of the policy divided by the policy, is equal to the gradient of the log of the policy. Okay? So that's just straightforward calculus. And this term over here is a very familiar quantity from statistics and machine learning. It's sometimes called the score function. But if you were doing something like maximum likelihood learning, this is the term which would come up. If you were just trying to maximize the likelihood of some action A, which someone gave you, you would follow this gradient. This is the thing which maximizes the log likelihood. And so the way to think of this term is this is the thing which tells you how to adjust your policy in a direction that gets more of something. So if you were to tell it the right action and you were doing supervised learning, you would plug in exactly this term for some particular supervised action here, and that would tell you how to get more of that particular action. So this tells you how to adjust your policy in a particular direction to achieve more of something that's good. And so we're going to use that, and what we see now is that by basically rewriting this gradient in this way, we're able to take expectations. Like computing the expectation of this thing is hard, but computing the expectation of this thing is easy because we have this policy here, and this is actually the policy we're following. And so we can take an expectation of this term because this is something we can actually sample from. This is the policy that we're actually following ourselves. So we'll see that in a minute. But just before we do that, let's consider this score function and understand what it looks like for two common examples. So perhaps the simplest example you should have in your mind, which we use for discrete actions, is the softmax policy. So the softmax policy is basically something where we want to have some smoothly parameterized policy that tells us how frequently we should choose an action for each of our discrete set of actions. So this is an alternative to something like epsilon greedy, or and the idea is to basically say what we're going to do is we're going to take some features, we're going to form some linear combination of features, for example, and we're going to consider that as like this some kind of value that tells us how much we'd like to take an action. So we've got features of our action in our state, we've got some parameters for those features, and then we weight those features by some weight, and we add it all together, and that tells us how much we desire that particular action A. And then what we do is to actually turn that into a probability, we just exponentiate it, and we normalize. So the idea is that the probability that we actually pick an action is proportional to the exponentiated value that we get when we take a linear combination of these features. So this is called the linear softmax policy. So a softmax in general is a policy that's proportional to some exponentiated value. And you can choose those values to be anything you want. And here we're just parameterizing those values in the simplest possible way by using a linear combination of some parameters with our features. So this is a very straightforward way to parameterize a policy in a discrete domain. So imagine we're doing Atari, and we want to know, should I go left or should I go right? Well, we'd have some features of going left, and we'd have some features corresponding to going right. We would weight each of those, and whichever one scores more highly when we make this weighted sum would get higher probability when we actually come to pick these actions. And now what we're going to try and do is find the gradient of this thing. We want to know, well, how do we adjust this thing so as to get more of the good things? So we need to know the score function, and the score function is very intuitive for this softmax. The score function, the gradient of this locked policy, is just the feature for the action that we actually took minus the average feature for all the actions we might have taken. So it's basically saying, how much more of this feature do I have than usual? And that's the score function. And so what we'll see is when we start to do these kind of policy gradient algorithms, what we'll actually end up doing is saying, if a feature occurs more than usual, that's what this thing is telling us, if it occurs more than usual, and it gets a good reward, then we want to adjust the policy to do more of that thing. Okay, so this is the softmax policy. I just want to give one more example of policy, which is the Gaussian policy. So in a continuous action space, like the IBO example, the commonest policy to use is a Gaussian policy. And what do we do with a Gaussian policy? Well, we basically just parameterize the mean of this Gaussian, and then you have some randomness around that mean, some variance around that mean, that says most of the time I'm going to take this mean action that's given by, say, a linear combination of some features, but sometimes I might take some deviation from that mean, and there'll be some variance like sigma squared, which could also be parameterized. You could have a variable variance. But the simplest case is to say now the action is selected according to some normal distribution with mean mu of s, where this might be a linear combination of our features. Like before, we've got features of our state and some weights for those features, and some variance parameter. So basically we get to pick the mean, and then we just add some noise to that thing to make it stochastic. And so if we were using a Gaussian policy, what would this score function look like? Well, the score function is basically, again, this tells us how to get more of a particular action. And here, again, we have something very similar to the last slide, where this tells us this is the action we actually took. This is our action A. And this is the mean action. This is the mean. So we basically want to know let's take the action we actually took minus the mean. That tells us how much more than usual we're doing a particular action, multiplied by the feature, and then we just scale that by the variance. So in both of these cases, the score function takes this form of sort of how much more than usual am I doing something. And that's quite intuitive when we start to look at these policy gradient updates. Okay, so that's just to give some intuition for what these score functions look like. Now let's talk about the actual policy gradient, this analytic policy gradient. And to do this, I'm just going to derive it for the simplest possible case, and homework, if you like, could be to extend this to the full MDP case. We'll talk about what it looks like, but I won't derive it for you. And the special case we're going to consider are one-step MDPs. So what do I mean by one-step MDP? I mean that you start in some start state S, you get to take one step, and you get one reward. It depends on where you were and what action you took, but then the episode terminates immediately. So there's no sequence in this case. It's just a one step, and then you're done. And you get some reward, and the goal is to pick your actions so that you maximize that reward. And the right thing to do might depend on the state and the action. So we'll see later this is also called, in subsequent lectures, a type of contextual bandit. And so now, if we were to try and solve this, we want to find the policy gradient. We want to understand how to adjust our policy parameters so that no matter what state we're in, we pick an action that's good. We want to adjust our way of picking actions so as to get more rewards. And the way we're going to do that is to start off by picking our objective function. So in this one-step case, all three of those objective functions we talked about become the same, essentially. And so our objective function is just to the expected reward under our policy. So we want to find the parameters which give us the most expected reward. And so we want to find the gradient of this thing and ascend the gradient of this thing, which will give us more expected reward. So if we're thrown into any state and we pick an action according to our policy, we want an expectation that to give us the most reward. And so the way we're going to do that, so let's just expand this out. So this is the expectation over the state that we start in, and this is the expectation over the actions that we pick under our own policy. So this is the expected reward. And now we're just going to plug in the likelihood ratio trick. So we're going to take the gradient of this whole thing. We want to know the gradient that gets us more reward. So the gradient of this whole thing, basically, the only term which depends on u is our policy. So the gradient of this whole thing, we can push the gradient right in to the gradient just of this term here, and expand that using our likelihood ratio trick. So this whole thing, the gradient becomes now the policy multiplied by the gradient of the log policy multiplied by the reward that you get. And so this is, again, now an expectation. That's the whole point of using the likelihood ratio trick. We start with something which is an expectation, you take the gradient, and you recover something which is still an expectation. So this thing is an expectation under our policy. So this is the expectation under the start state, an expectation under the action that we pick of the gradient of the log policy multiplied by the reward. So it's just the expectation of the score times the reward. So after all that, we've basically come back to something very simple, which tells us that if we want to increase our objective function, if we want to get more reward, we just need to move in the direction that's determined by the score times the reward. Okay? And so again, this tells us how to adjust our policy so to get more or less of something, and this tells us whether it was good or bad. So if you have a really big positive reward, you want to move more in the direction that gets more of that thing. If you have a really low negative reward, a really large negative reward, you want to move in the opposite direction to your gradient. Okay? Any questions? Stunned silence. Okay. So, yes?
Can I just ask, this is model 3, right?
Yeah.
And we have the capital R, which means that we know the rewards and everything.
Okay, so notation, this capital R is the random reward, the actual reward that you experience. This curly R is the reward function for the MDP. So we've expanded this in terms of something which actually is described in terms of the dynamics of the true MDP, but we brought it back again to an expectation where we only need to look at the sample reward that the agent actually experiences. So this is completely model-free. So model-free, what this means is if we want to estimate this expectation, we just take an action from a given state, we compute the gradient of this log policy, which we know because it's our own policy, and we multiply it by the reward that we actually experience. And that gives us a gradient step, and we follow that gradient step. So it's model-free. Good question. Okay, so we want to do the same thing in MDPs, multi-step MDPs, not just these one-step things. And to do that, we actually just need to do one trick, which is to replace this instantaneous reward that we had. So we were multiplying the score by the immediate reward. And to do a multi-step MDP, all we need to do is actually replace this immediate reward with the value function, the long-term reward. And that actually turns out